Hello friends, welcome to this lecture on computer-aided power system analysis. In the last lecture, we have discussed the concept of chi-square distribution, and we said that this estimated value of the objective function follows the chi-square distribution, and then we have also discussed the need of the bad data detection. So, in today's lecture you would be looking into this aspect of bad data detections. We said that this f hat we said that f hat follows the chi-square distribution. Now, although f hat follows the chi-square distribution, because it is a random value and because it follows a certain distribution, probability distribution function, so then therefore, it will also should have a certain parameters. So, we would like to know that what is the mean value of f hat. So, what we want to know that what is the value of expected value of f hat. So, that would be obviously something like this. So, that would be the case. Now, we also know that expected value of, we have already seen in the last class or rather the last lecture, that E hat transpose is actually an matrix R or dash, and we have also seen that this quantity, that this is an m cross n matrix. So, this is a square matrix. So, then therefore, and because it is a square matrix, so then all quantities that E I hat square for all I is equal to 1 to m are the diagonal elements. Correct. So, these are all diagonal elements, and this matrix is also an m cross n matrix, that also we have already seen. So, then therefore, this is also an m cross m matrix. So, this is also a square matrix. So, then therefore, we can say that expected value of E I hat square is actually R I dash, that is the diagonal element of this. So, then therefore, we can say that expected value of Z I minus Z I hat square is equal to R dash I, that we can say. So, then therefore, I can say that expected value of Z I minus Z I hat square by R I dash, that is equal to R I dash by R I dash is equal to 1. Now, if I utilize this into this expression, so from there what do I get? We get that expected value of f hat. So, then therefore, expected value of f hat is expected value of 1 to m Z I minus Z I hat square by sigma I square, that is we have already seen. Now, we write that this we can write as R I dash into R I dash by sigma I square. This entire quantity is within this summation. So, this is the expected value of this. So, then therefore, this is nothing but we can write down that I is equal to 1 to m expected value of z I minus z I whole square by R I dash into R I dash by sigma I whole square. Now, this is something into this. So, then I can take it out. So, then therefore, I can write it down I is equal to 1 to m R I dash by sigma whole square into E z I minus this would be hat, sorry, z I hat square must write it more properly, to expected value of z I minus z I hat square by R I dash. Now, this quantity we have just now seen that this quantity is equal to 1. So, then therefore, it turns out to be that I is equal to 1 to m R I dash by sigma whole square. So, then therefore, this is a very important relation. Expected value of f hat, that is the estimated value of the objective function, is given by I is equal to 1 to m R I dash by sigma I whole square. So, this is a very important, relation. Anyway, so by this we can calculate that what would be the mean or average value of the estimated value of the objective function. Now, let us again come back to our topic of discussion, that we would like to estimate, or rather we would like to find out that which particular measurement data is bad. Bad means that which particular measurement data has got unacceptably large value of error. So, now what we do is for that we do follow some simple steps. So, we write that the steps for bad data detection is like this. Steps for, we have already covered all the theoretical background. So, now we are ready to write down the steps for bad data detection. So, what is the steps? Step sheet, estimate x hat, that is we get the measurement and etcetera, estimate x hat, or rather calculate x hat, we can write down calculate x hat. From that we can calculate z hat, z hat is h into x hat. From that we can calculate E hat, E hat is z minus z hat, can calculate. Once we get E hat, then we calculate f hat, f hat. So, that we know that how to calculate. So, calculate f hat. Once I calculate f hat, then we now consult our chi-square distribution curve. Now, to consult our chi-square distribution curve, first we determine what is the value of k. k. What is k? K is degree of freedom, degree of freedom. Now, how do I determine the value of k? K is nothing but m into n. What is m? M is the number of measurement, it is the number of measurement and what is n? N is the, or we should say total number of measurements, and we also should say it is total number of states. So, we know that what is the total number of states, and we already know that how many meters I have put. So, k is equal to m minus n. Next step is choose an appropriate value of alpha. What is alpha? Alpha is the alpha is basically the probability which I wish to maintain. Alpha is the value of the probability which I wish to maintain. So, then what is the seventh step? Find out the threshold value from the chi-square distribution curve corresponding to the values of k and alpha. So, we find out that what is the threshold value. We have already shown in the last lecture that corresponding to any particular combination of k and alpha, there is a certain threshold value. So, we find out the threshold value. Then what we say, if let this threshold value is denoted by let this value be denoted as, let us say this is C k alpha. This C stands for this chi-square distribution curve, k and alpha are those values. If, so now after this we do, if the value of f hat is less than C k alpha, then we say that there is no bad data in the system. And if this value, if greater than C k alpha, then presence of bad data is detected. Bad data is detected. Now, what is the philosophy for this? So, I mean these are the very simple steps. Now, what is the philosophy for it? Please understand that again let us look at this curve, and this curve is looking like this. Let us say this is the curve, and we have some value of alpha, and this is my value of alpha. So, this area is alpha and this value is C k alpha, this value is C k alpha and this is alpha. and let us say this is particular value of k. So, what does it mean? Now, suppose if say alpha is equal to 0.01, suppose if I say for alpha, for example, in our table we said that for k is equal to 2 and alpha is equal to 0.01, C k alpha is equal to 9.21, that we have already seen in the last lecture. So, what does it mean? It means that the calculated value of f hat has got only 1% chance that it will have a value of more than 9.21. Now, we need to understand that what is the occasion in which this value of f hat will keep on increasing. Now, please note that f hat is nothing but this quantity. So, then therefore, this value of f hat will only increase if this value of E I hat increases. After all, sigma I square is constant. So, then therefore, f I hat only increases if this value of E I hat increases. E I hat will only increase if there is large difference between the actual measurement value and the estimated measurement value, and this large difference will only happen if and only if some measured data is absolutely erroneous, and that particular erroneous data makes all the estimated states to be quite erroneous, which are not at all close to their actual value, and because these estimated states are quite erroneous. So, then therefore, this estimated value of the measurements become quite erroneous, and because this estimated measurement values become quite erroneous. So, then therefore, this vector E hat will also become quite erroneous or rather large. So, then each and every element of E I hat would be large in magnitude. So, then therefore, f hat would be large. So, then therefore, this probability is pretty small, it is just 1%. So, then under normal condition it is most likely that the calculated value of f hat will be always less than this particular threshold value of 9.21. But if this value calculated value of f hat crosses this threshold value, that means that this calculated value of f hat is quite high, or in other words, at least some value of E I hat is quite high. So, that means there has to be, there is probably at least one meter which has gone bad. So, we detect the presence of bad data, but now the question is, how do I detect that which one has got bad data? So, for that what we do is that we simply calculate, we simply calculated the value. Now, to detect bad data, then what we do is, so in this example, if we look at, if we do remember in the first case, our basically our measurement values were so in the first case, in the basically last lecture, we have considered two cases. We have considered a simple circuit, and we have considered two cases. In the first case, there are some meters and there are some values, and for that values we have calculated all the state vectors, and once we calculated all the state vectors, then we have calculated this E hat vectors, and those E hat values were E1 hat was is equal to 0.00877, E2 hat was given by 0.00456, E3 hat was minus 0.02596, and E4 hat was minus 0.00070. So, these were the estimated errors in the first case, and we have also said that our our weights were omega W1 is equal to W2 is equal to 100 and W3 is equal to W4 is equal to 50, that we have already seen, we have already taken. So, when I utilize these values, we get this is the value of f hat. So, it is 100 E1 hat square plus 100 E2 hat square plus 50 E3 hat square plus 50 E4 hat square, and if we do substitute these values, we get these values. Now, in our example what we had, we have got total number of measurement was 4, because there are 4 meters, 2 ammeters and 2 voltmeters, and my total number of state was 2. So, this measurements were V1, I think this was VA, VB and I1 and I2, and the states were V1 and V2. So, then therefore, total number of measurement was 4 and the number of states is 2. So, then therefore, K is equal to 4 minus 2, that is 2, and we have taken, let us say, alpha is equal to 0.01, and corresponding to this C K alpha is 9.21. Now, we can see that the calculated value of f hat is much less than this threshold value 9.21. So, then therefore, we say that there is no bad data is detected. Now, this was the case when our last measurement value was 5.01 volt. So, this is for VB. Now, suppose we have got another case, we have shown another case where all three other measurements were the same, but now Z4 was 4.40 volt. So, for this we have also shown that the value of errors was estimated errors were 0.06228, then E2 hat is 0.15439, E3 hat is 0.05965 and E4 hat is minus 0.49298. So, these were the values, and now when I put these values, I get that f hat is 15.1009 and 15.1009 is much greater than 9.21. So, then therefore, there is an bad data is detected. So, now the question is, how do I calculate, how do I find out that which one is the bad data? So, for that what we do is we actually calculate. So, that is what we are saying, we actually calculated the value of E1 hat into root over R11 dash. Now, here we need to remember that expected value of EI hat square is actually R II. So, we said that expected value of, we said that Zi minus Zi hat square divided by RII is equal to 1, that we have already seen. So, then what we are actually trying to do, but this is the expected value, but then what is, but in that case what we calculate is, we actually calculate when there is an bad data is detected, we actually calculated something called, EI hat divided by RII. So, we calculate the so, we calculate Zi minus Zi hat divided by RII root over. Once we calculate this value and then we find out that which one is the highest and which one is the highest, that one we do take as the. So, now what we do is that we do calculate E1 hat by root over R11 dash. So, this we calculate. So, from this we calculate this, from this we calculate this. So, then we are simply weighted value of this estimated errors we are calculated, this is called weighted values. So, then we calculate these weighted values E1 hat by root over R11 dash, then we do calculate E2 dash by root over R22 dash, E3 dash by root over R33 dash, E4 dash root over by R4 4 dash. Remember these quantities are nothing but the R1 1 dash, R2 2 dash, R3 3 dash and R4 4 dash are nothing but the diagonal elements of the R dash matrix. Because these are the diagonal elements of the R dash matrix, so then we can easily calculate them. So, this is already known. So, from this we calculate these values and we find out that these are the values. Now, out of this which one is the highest? Out of this magnitude wise this one is the highest, although this is positive, this is negative, but as far as this magnitude is concerned this is highest. Because this is highest, so then therefore, we conclude that this is the bad data. So, this data must be the erroneous. So, we simply discard them. So, once we discard them, then after that, so now we have got actually 3 measurements with us. So, because we have got now 3 measurements with us, so then we have got now this H matrix is only 3. So, after that we again do all these calculations. Once we do this x 1 calculation, x 1 hat, x 2 dash, after that we calculate E 1 hat, E 2 hat, E 3 hat this, and then we again calculate f hat is equal to this, which is 0.0435. And now what happens in this case? In this case, now my m is actually, now my m is 3 and n is equal to 2. So, my k is equal to 1, and if I keep alpha is equal to 0.01. So, then therefore, if I look at this graph. So, for k is equal to 1 and alpha is equal to 0.1, this threshold value is 6.64. Because this threshold value is 6.64 and this is less than this. So, now there is no bad data. So, therefore, these estimated values are reasonably close. Please note that when we have done our estimation with 4 measurements and when we said that there is no error, these estimated values were coming out to be quite close to 16 and 8. Their true values is 16 and 8. And now, when we have already detected one bad data and removed it and done this particular state estimation with this value of only 3 measurements available. So, then therefore, we have got again this same values which are again close to this estimated quantities, or rather which are close to this true values. So, that is how we do this bad data detection. So, we will continue with this particular aspect in the next lecture, especially the reason for this calculation. This reason for this calculation is not still explained in a great detail. So, in the next lecture we would be looking at this aspect as we would be actually looking at this aspect in the next lecture in a more detail. Thank you.